Hey guys, happy Friday. Today we have a lab and it's going to relate to the Beer-Lambert law, which is from topic 3.13 or 3.13 from last unit. This is a really important lab that we need to kind of work with and hopefully you guys can understand what I'm up to here, and we'll analyze the data again when I'm all done. But this is an important one because these techniques and these skills that we learn from this lab are very necessary for a later lab this year in Unit 5. So hopefully by watching this video and going through the data and the worksheet that I have for you guys that goes along with this, I'm hoping we can make some sense of it and yeah, we can conclude what we're trying to figure out here. So the goal for today in this lab is to figure out how much blue number 1 dye is in Gatorade. All right, and the formula for blue number 1 dye is this thing. Okay, kind of crazy. It's this big, huge molecule. And there's negatively charged regions here. There's a sulfur with oxygens. This is called a sulfate or a sulfite group. And there's sodium ions as well. Like it's a salt, basically. It's this huge, massive salt compound with cations and negatively charged anions. You'll see there's a plus charge here, a minus charge here. It's complicated, right? That is the blue dye molecule that's in food. So we are going to, sorry, I got to move my face for a second. So we're going to try to analyze how much blue dye is in Gatorade by using spectrophotometry. So as a part of the Beer-Lambert law note sheet, we talked about spectrophotometers, and we're going to use one today. I have one right over here. I'll show you in just a second. You can maybe hear it humming in the background. That's if the humming noise, that's the instrument, not something else. So anyway, so spectrophotometry, spectrophotometry is a method used to measure how much a chemical substance absorbs light by measuring the intensity of the light as it passes through. We've talked about this a little bit, right? I gave you that generic kind of setup of how this machine works. But really what we're going to do is we're going to set up a known profile of blue dye and the concentration of those different molarities or the different solutions. And once we gather the profile of the known molarities of blue dye, we'll then analyze or use our Gatorade sample and then test that for absorbance as well to see what that measure, what it reads, and then we can use our data to analyze the unknown and hopefully solve for the molarity or the concentration of blue dye in Gatorade. So today we're using an instrument called a Spec 20. It is a spectrophotometer, and essentially it's a visible type of spectrophotometry. So spectrometry, I should say, really. So the word photo is implying visible light. So we talked about the electromagnetic spectrum, and there's all different types of spectrometry that use different regions of the electromagnetic spectrum. This is using visible light. Today we're going to set it at 560 nanometers. So 560 nanometers is green-ish, bluish, greenish. It sounds kind of weird that we would use green light for a blue dye. But if we use a different wavelength, a more blue wavelength, it's actually so intense that it goes off the chart on the instrument, so we can't get a good reading. So we're going to use 560 because it's in that nice sweet spot where we get a good reading of how much blue dye is there, but we're not going off the chart of the instrument. So if you're curious, if you looked up what color this nanometer, this wavelength is, it's actually green, but we're testing blue dye. And again, the reason why that is if we used blue, it would be off the chart and we couldn't get a good reading at all. So we have to use a slightly adjacent wavelength just to make sure we get good readings. All right, so on your sheet, we will first need to calculate or collect data for a range of known concentrations of blue dye. I'm going to get that set up in just a second. I'll have you watch me do that, and I'll go through it and kind of explain what I'm up to. And then once we've gathered this data, we're going to need to graph it. Remember, we have the Beer-Lambert law. It's on the next slide. We need to know what the absorbance and the concentration are, and we can set this up in a linear format. So we will do that in just a second, but we need to collect these concentrations first, or these absorbances or absorptions first, but we got to set it up. So here's the Beer-Lambert law. Okay, A equals EBC. A is absorption again. Absorption is how much light is absorbed as it passes through our solution. The instrument's going to tell us all of that. We also have the molar absorptivity. That's that little lowercase epsilon. That is a constant that compares our two variables that we care about, absorbance and molarity. B is path length, it's 1 centimeter as always, and C is concentration. So this is what we need, and this is eventually what we're going to graph. speaking of which, here's what we're doing. What should our y-axis be? What should our x-axis be? What's the slope of our plot represent? We're going to come back to this in just a little bit. Let me get set up, and yeah, let's get this experiment rolling, and then we'll kind of consider these questions. And I hope you know the answers to these questions, because this all was a part of 313. But anyway, let me get set up, and I'll pause it and come right back. All right, I'm going to go full screen here, and I'm going to kind of show you some things here. So I'm using my computer, so I'll try my best here to get you a decent view. But this is the spectrophotometer. Nothing too exciting. It just kind of looks like a boxy white instrument, but what this is going to do is this is going to allow us to measure those absorbances of these varying concentrations. So what I also have is I have blue dye. This is a known molarity. Now this flask is called a volumetric flask. Okay, it has a really long neck, kind of a bulb here on the bottom, but this thing is calibrated to exactly this precise volume. A volumetric flask is one of the most precise pieces of glassware in a laboratory. So when this says 500 milliliters, it actually means 500 milliliters. This isn't an estimate. There's a line right here, which is probably impossible to see on the computer, but that line is precisely 500.00 milliliters. It is super precise, very, very precise. This is more precise than a graduated cylinder, as a matter of fact. So I've got my blue dye. The molarity of that is 7.2 times 10 to the negative 6th. It's on the worksheet that goes along with this. So I have posted a worksheet in the plans with this video, and that worksheet is going to kind of have a data table on it, and we're going to fill that out in the near future. But what we need to do is we need to set up these varying molarities. So I just have a beaker. I'm going to take some of my blue dye here and just fill it up, because I'm going to use this. We'll use about that much. That should be plenty. And I also need distilled water. This is just a wash bottle, but what I'm going to do is I'm going to take the top off here, and there's plenty of distilled water in there for me to use. So we need to make molarities. What I'm going to do is, hold on. All right, sorry about that. Let's try this again. So what we're going to do is we're going to make these solutions, all right? And what I have is this is your note sheet, or your sheet that goes along with this lab, okay? And in the middle there, I have a data table that's very partially filled in. And you'll notice that I have trial 1, 2, 3, 4, 5, 6, 7, 8. Trial 1 is filled in completely. What trial 1 is, it says V1, which says V1 stock. Now, stock is the blue stock solution, okay? Meaning the solution that I'm giving you as a part of this lab. The molarity of that, which is in the 4th or 5th column, I guess, 7.2 times 10 to the negative 6th, like I had said earlier. Now, the next two columns, I have V subscript H2O, and I have B subscript 2. V2 is going to be the total volume for all of these solutions. So what we're doing, again, is we are setting up different molarities of blue dye, and we're testing them. We're then going to graph those different molarities to get a nice relationship of Beer-Lambert law. And once we know that, then we can solve for our unknown. So what we first have to do is make up these solutions so that we have a nice range of blue dyes, and then we know their absorbance for. So we have a little bit of math here to fill in. I didn't fill in a lot, but what I'll say is the first column there, which is V1, which is stock, the stock solution, we're going to make 8 different vials or 8 different test tubes of this solution. The first one is pure stock solution, 10 milliliters. The next one is going to be a mixture of stock solution and distilled water. We are making a dilution. We're adding water to it to lower its molarity or lower its concentration. The total volume, which is V2, is always going to be 10. Okay? So for that column, you can write in 10.0 all the way down. The total volume of all of the solutions that I'm going to make is 10 milliliters. The first one I make is 10 milliliters of blue stuff. The very last one I make is 10 milliliters of water and nothing else. Okay? So this is what I've done so far, if you can see. Right? And the math is very, very simple. The total's 10. So for the next one I did it, 8 milliliters of blue, 1 milliliter or 2 milliliters of water, total of 10. The next one, 6 milliliters of blue, which leaves us with 4 milliliters of water, and a total of 10. So I'm just going to fill this in all the way, and these are the solutions that I'm going to make. Okay? I am going to make different varying molarities of dye, and I'm going to use different milliliters. Now, the way I'm going to do this is I have my blue dye in the beaker right there, and I have my distilled water here in this wash bottle, and I'm going to use syringes today, okay? I could use graduated cylinders, but it's a little pickier, takes a little more time, so I'm going to use these syringes. These are needleless syringes, so there's no needle here, but these are just as accurate, and the key to using these, which again, I know if you were here in the real lab, I would make you do it, but the key to getting a good volume on these is pulling up the plunger and giving a nice little air bubble in there first. And the reason why that's helpful is because now, when I pull this up and I try to get my 10 milliliters, uh-oh, too much air. Let's try again. Let's go right there. That's perfect. Okay, now when I draw the blue dye in here, I can actually see the meniscus. Okay, if I had left the plunger all the way down with no air bubble, I would have no clue where the meniscus is, and then I'm kind of relying on like that line of the plunger, or is it that line of the plunger, and it's hard to tell. So this is a little easier. I make that bubble, so now I can see the meniscus of my volume. I'm going to get this down to 10, and this is my first solution. What I have over here is a test tube rack. Okay, all it is, you know, a rack for test tubes, nothing too exciting. But what I'm going to do is from left to right, I'm going to make up these solutions. Okay, so my first solution is 10 milliliters of stock solution, and I'm going to add that. And there we go. Okay, almost fills it up, not quite. That's a good volume. All right, for the next one, I need 8 milliliters of stock solution. I'll make the bubble, pull this up, and I'm going to get 8. Get rid of the air bubbles up top. Maybe. Go away. And I overshot it just a smidge. There we go, 8. I'll add that to the second test tube. And then I also need 2 milliliters of water. Okay? So again, the second one here is more dilute than the first. This ain't gonna work. I'll be right back. I'm going to need a test tube, or a beaker, rather. Not prepared. Okay, I got my beaker of water. Let me continue forth here. And I'm going to pour some water in there. That's the whole point of this thing, so I can see what I'm doing. And let's grab 2 milliliters from this water. There we go. Perfect. I'll add that there. And my second test tube is ready to go. It is dilute, more dilute than the first, and then we're going to keep on going. So I could bore you and I could let you watch me do this for, 10 minutes, but let's not. I'm going to pause it. I'll be back in a second. I'll get all of these solutions made up based off of the instructions on that sheet, and then I'll explain how I'm going to use the instrument and go through the steps in that process. All right, so they're all made up. I've got my blue solutions now. From left to right, you can see even on the screen that they are getting progressively lighter blue because they're more dilute. What I'd like you to do is I would like you to do the calculations to get all those molarities. Now, the dilution equation, which I think you did last year, again, I didn't teach chem last year, so I'm not quite sure where you guys were at and what you all learned, but there's an equation, which is a dilution equation, which is very, very simple. It is M1 V1 equals M2 V2. All right? And this data table, I kind of set it up on purpose the way I did because in the description, I have that M1 is 7.2 times 10 to the negative 6. In the data table, I have V1 as this column, and this column is V2. So you have 3 of the 4 pieces to get the molarity for all of these. M2 is your final answer. So all you would need to do, plug in 7.2 times 10 to the negative 6 here, plug in the appropriate volume of the stock solution from this column here. Okay. Now, the volume, again, changes. 10 milliliters up here, 0 milliliters down here. It just depends upon which one you're doing. M2 is what we're trying to solve for. V2 is always 10. Okay. And as long as both volumes on both sides are the same label, it doesn't matter. So we can absolutely use milliliters. For the first one, or for the second one rather, I would plug in 7.2 times 10 to the negative 6 multiplied by 8 equals M2, which I don't know, multiplied by 10. And then I would just solve for M2 and get the molarity. Okay? So please do that calculation for each of these. Let's go to the next step. The next step is actually using the instrument. All right? So let me turn my camera a smidge over here again, and I'll try to get a decent angle for you guys. But what I need is this little guy. Now, this hardly looks any different than the ones that I have in the test tube rack, but this is a cuvette. This is what gets placed inside the instrument. Okay? This is precisely 1 centimeter in width, because we want our path length to be 1 centimeter. So what I need to do first is I need to calibrate the instrument. Okay? The way I do that is by adding water. So I'm going to take my very last test tube in this series, just pure distilled water. I'm going to fill this thing up. And when I fill it up, I'm going to fill it up to about the dot. Okay? So if you were here, I would absolutely warn you about this. You can see it's filled up to the dot there. But these test tubes hold 10 milliliters. A cuvette cannot hold 10 milliliters. It's close, but it'll overflow just a little bit. So I don't want to overflow this. That's not good. So I'm going to fill it up right there to the dot. The next thing I'm going to do is I am going to wipe this down. So I just have some tissue paper, okay, and I'm going to wipe down the outside of the cuvette. And the reason why you want to do that is to make sure that any fingerprints or any smudges aren't messing with our absorbance reading. All right, so I've wiped this down. Now I'm going to come over here and I'm going to put this into the instrument because I need to zero it. Okay, now there's no blue dye in water, right? That makes sense. So I want my instrument, when I have pure water in there, I want it to read 0, right? That makes sense. There's no blue dye. So I've got to mess with this a little bit, and I'm going to change the dials until I get to 0. Okay, this is a finicky little thing, so I got to be a little careful here, and I'll show you when I'm all done that we got it to 0. All right, sweet. Bring you guys over here. Okay, there's my instrument. On the left, you see 560. The next one says 0, or rather 0.00000. That's good. That's pure water. It's perfect. Now, I'll show you one other thing. Okay, I'll open the cap here. This is where I'm putting it in. All right, and when I put it in the instrument, there's a line on the cuvette, and there's a line here on the top of where I put it in. I don't know if you can see that, but maybe you can. And I want to line those two up every time, because the idea is I don't want my light, my wavelength, passing through a different part of the glass, because it actually can mess with the reading. So every time I put this down in here, I want those lines perfectly aligned. I close the lid, and then I read the absorbance. Now, it's drifted just a tiny bit. We're at 0.001. Let's see if I can get it back. Oop, wrong way. And if you can see how little I'm moving it. Oh man, now it's fighting me. I'm losing. All right, there we go. By the way, -0 just means it's on the negative side of 0. So there's a decimal point way over here that we can't read, right? So it's 0. All right, cool. We're good. I take that out. All I need to do for the others is fill up my cuvette with that color dye and take some readings. Okay? So I'm going to start doing that. I'll show you a couple here. Let me dump my water back where it belongs. And now my cuvette has some residual water in there, right? That's not great. I don't want that residual water in there. So all I'm going to do, I'm going to go over here. I'm going to just shake it out and get all that water out of there as much as I can, because I don't want that to dilute my next sample, right? And it's not perfect. If you can see, there's tiny little droplets still in there, but it's not too bad. Those tiny little droplets aren't going to throw my data off to the point of messing everything up. So let me get my next sample. My next sample here is the full concentrated dark blue dye. I'm going to measure that first. Let me pour that in there. Up to the dot. Again, these test tubes can hold 10. The cuvette cannot. All right, sorry, herky-jerky today. Let's try this again. So I'm wiping my blue dye down, and we're going to put it in the instrument, and let's get our absorbance. So I line up the lines, I close the lid, and the absorbance for the very first most concentrated pure blue dye from the stock solution is 0.920. I'll write that down right there. Oops, hold on. There you go. All right, so onward and upward. Let's get the other ones. I'm going to keep going. I'm going to pour my blue dye back where it belongs. Oop, and I'm spilling. I'm going to try my best to dry this out. I'm going to tap out the blue dye as much as I can, and then I'm going to shake it. Okay, on to the next one. Now, the next one, I had water and I had blue dye, and I diluted it. Now, it looks pretty well mixed, and I think it's not too bad, but I'm going to do this. I'm going to pour once to the cuvette, pour it back to the test tube, and then pour one more time back into the cuvette, just to make sure it's actually fully mixed up, right? We don't want to not have a homogeneous liquid there. So, all right, second sample now. Same thing. I need to grab a little bit more tissue paper here and wipe this down. And let's get the second one. The absorbance for the second sample is 0.790. Oops, I can't write. 0.790. We'll keep going. Pour this back. Try not to spill this time. Successful. We'll get as much of that off as we can. I'll kind of tap it off onto the tissue paper and then shake it. On to the next one. Again, we'll do a pour back and forth just to ensure that it's actually fully mixed. We want to make sure it's homogeneous. And if it's not, you'll know. If you put a non-homogeneous mixture into the spectrophotometer, it'll never stabilize. Those numbers will just keep on jumping all over the place. Let's wipe this down, make sure my fingerprints are off of it. Get a third reading. The third one is coming in at 0.648. Onward and upward. Grab the next, same thing. Wipe it down. Let's get a reading. Point 462. And here's what I'll do. I have 3 more to go. Let me pause it, spare you the excitement of this, and we'll get you your data in just a second. Okay, so I've got everything I need. Here is your data for absorbance. The first one, the most concentrated one up top, 0.92. 0.79 for the next, 0.648, 0.462, 0.394, 0.298, and 0.194. The very bottom one is pure water. That's what we calibrated the instrument with, and that's just 0. All right? Now, we're going to need to take this data and graph it. We're going to need to find our molar absorptivity. So I'll show you how to do that in just a little bit. All right, so we have all the data we need. Now let's turn it into a graph. All right, just as a refresher of why we're doing this, why we're graphing it, and what this is going to do for us. Okay, so this is the Beer-Lambert law, or the Beer-Lambert equation, right? We have absorbance, molar absorptivity, path length, and concentration, aka molarity. Okay, now we have just collected data. Okay, you can't see it because I'm in the corner now. I've shrunk my screen, but you have collected data. We have data on absorbance, and we're able to calculate the molarity of M2 for all of these different trials, or all of these different samples that we ran with the blue dye. So let's go to Google Sheets. Okay, in the plans, I had a link. You might have already opened it. What it was is a link to the Beer-Lambert law, or the Gatorade lab Google Sheet. Okay, we're going to use Google Sheets to make our graph today. So if you have that open, let me switch over to mine. Okay, it just looks like this. Now, what I've done for you, I've been a little nice. I have organized the data. Okay, the data right here, we have absorbance, we have concentration. These are the correct answers when you're doing the dilution problems. Okay, the M1V1 equals M2V2. So this is our data. These were the concentrations of blue dye, and these were the absorbances that the spectrophotometer gave us. What I want to do now is I want to insert a graph. So I'm going to highlight my data. I'm going to go to Insert. And when I do, I will go to Chart. Now, when I click on that, it's going to give me some options, and you'll see it actually did a pretty good job. It actually picked what I wanted it to pick. I hope yours does the same. Sometimes this program can be a little picky, but anyway, yeah, this is exactly what we want, okay? So now I'm going to go to Scatter. Perfect. It gave it to me. And I want to make sure of one of a couple things, okay? Remember, with the Beer-Lambert law, let me switch back really quick. We have A equals EBC. When I set this up in terms of the slope-intercept form of a line, this is my y, this is my x. Y equals mx. Our y-axis should be absorbance. Our x-axis should be concentration. Okay, let's go back to the Google Sheet. Did it do that? Oh, it did not. Sad. We got to fix it, okay? So here's what I'm going to do. I can go back in here in the setup, and I can switch which is what. So you'll notice under the x-axis, I clicked on that, and it had two choices. I'm making the x now my concentration, and I'm making the y now my, come on. Oh, where is it? There it is. I'm sorry, I can't see. My absorbance. Now, the labels didn't switch, but the numbers did. Okay, so let's fix the labels, because the numbers got flipped. You'll notice this is concentration, right? Our concentrations were very, very small. And this is absorbance. Our absorbances were between 0 and 0.9. So the numbers are good, the labels are not. So I'm going to switch this. I clicked on that title over there, and I'm going to switch this to absorbance. I clicked on the title down here, and I'm going to switch this to concentration. And if you want to be more specific, you could put molarity in parentheses, because that's what it is, right? This is molarity. And then you'll notice that our title is backwards as well. We'll do absorbance versus concentration. I can't spell. There we go. Okay, so now this is good. I'm going to put this in the center. That bothers me. I don't know why, but there's a little centering thing over here, so I just click that and make it centered. And now this is our graph. It looks pretty linear, right? I think that's the idea. We want this to be a linear graph. But let's check the data and make sure that maybe, you know, let's see how we did, I guess. So let me go and let's see if I can find it here. Well, I'm sorry, I need to be on my data. So let me click on my data. There we go. And I'm under series now, okay? And it has absorbance listed. Don't worry about that too much. The blue dots. I clicked on a blue dot, and then it dropped down to this series. What I want to do, I want to go down further, scroll down a little bit. There's a button called trend line. I want that, okay? And I want a linear trend line, okay? You can label this as well. You can throw in the equation. That's a good thing. We need the equation. That's what's going to help us solve for what we need to solve for in just a little bit. Now, a couple things of issue here, all right? The first thing is you'll notice that here is our intercept, right? 0, 0 with the water, but the rest of our data is kind of above it, and if we ignore that first data point, we're going to do much better. So let me ignore that first data point. This is a much more closely representative slope of our graph. Okay, this is more linear than when I have that intercept forced into the data. So I'm going to do it this way. I deleted that bottom line, and you can do the same, and it will take it off your graph. Okay, and we're going to use this as our line. Now remember, our equation is A equals EBC. A is absorbance. That equals 111,943 x plus 0.138. So we have this y-intercept. We'll keep it for the in terms of the data, okay? But in reality, this kind of should be 0. I'm not allowing it to be 0 because it makes the line a little nicer. But anyway, kind of should be 0, but let's keep this data. So this is our Beer-Lambert equation. What we have just done, and I'll see if I can type it in here. Let's switch color just to make sure we can see it. Okay. What we have is absorbance equals 111. Was it 111? Hold on. 943 multiplied by concentration. Okay. So I'll put parentheses around it. Maybe that looks a little better. There we go. So we have this equation. All right. The slope is this. We have an intercept. I suppose I should probably put that in. Okay. 0.138, I believe it was. Let's scoosh this over just a smidge. There we go. Okay. And what this is this is our Beer-Lambert law specifically for blue dye at 560 nanometers. All right. This is our data for this lab, for this dye at this specific wavelength. This number means nothing to anyone except for us and our data. And if you were doing this in the real lab and you were all doing this and working in different groups, you would get different numbers for your slope. They'd all be kind of close, right? I would assume they're all in like the 110,000 range, somewhere in there. 112,000, mine's pretty close too. But they're not going to be the same. And that's okay. That's what data is, right? When you collect data, it's not going to be perfect. That's how life works. So this is our equation from the data that I collected. Now, what does it mean? Well, what it means is now if I put another sample into the instrument, I'll know its absorbance because the instrument will tell me. The spectrophotometer will give me the absorbance. And from that absorbance, I can solve for concentration. So what we're going to do is test Gatorade. That was the whole point of this lab, is to figure out what is the concentration of blue dye in Gatorade. Well, now we have a way to solve for that. Now we have the means of solving for that concentration. So let's go back to the instrument. Let's throw some Gatorade in the cuvette and see what we get for an absorbance. And then we can plug the absorbance into our expression, use the slope, or in other words, the molar absorptivity, right? Because we know our path length B is 1. So the slope is our molar absorptivity. It's, you know, this huge number, really. I guess if we could shrink it down for sig figs, 1.12 times 10 to the 5th. Okay. Inverse centimeters, or sorry, 1 over centimeters, 1 over molarity for the label of that, if you remember that. But let's do this. Let's get our final problem. What I want from you, okay, and what I would like for you to do is I would like for you to turn in this sheet with everything filled in. I have another column here at the tail end, which is absorbance over M2. So you'd take the, what is that, 5th column divided by the 4th column, okay? This is like a little snapshot of your molar absorptivity. In theory, that very last column should be constant. Spoiler alert, it's not going to be constant. But anyway, do that calculation if you could. Fill in all your molarities if you could. I would really, really, really like you to do what I did on the Google Sheet, meaning I gave you kind of just the data, and then I put in this graph, and I switched some things, and you were watching and following along. I hope you followed along with me. I would like you to do that. I don't really want to collect this from you because it's just a giant pain, and I don't want you to print it. I don't want you to take a picture of it. I don't want to get a whole bunch of shared Google Sheets with me of the exact same thing. Ugh, I don't want it. But I want you to try it at least, because doing this Google Sheets. Doing this in Google Sheets is a useful skill to know how to make a graph, to manipulate a graph, to change the labels and all that good stuff. I went rather quickly, but it is a video, so you can go back and watch again if you need to. So all I want is a picture of your data table, whether that is on this sheet or not on this sheet is perfectly fine. Again, if you're not printing this or you don't have printing capabilities, you're welcome to work off to the side. And I would also like the molarity of Gatorade down here. Now, you can only get that if I give you the absorbance. So I'll shut up. Let's go take the absorbance of Gatorade, and then we'll call it a day. All right. So here I am. I've got my Gatorade. Let's crack this thing open. And let's get a measurement. My instrument is still zeroed. I have reset it up. So now I'll pour some Gatorade into the cuvette. It wasn't too bad. I just spilled a tiny bit. Okay, and we will wipe it down, make sure there's no fingerprints on there like we always do. And we'll put this in the instrument. Line up the lines. And I am getting an absorbance of 0.200. 0.200 is what I'm getting. By the way, I didn't really show you this when I was doing the rest of it, but that's how you read it, right? It just changes based upon what you put in there. Ooh, it's drifting now. All right, we're back to 0.2. And that's it. So let's record that 0.200, and that's your absorbance that you need to solve the final problem of the concentration of Gatorade. Okay, so let me leave you with this, okay? Here's what I would like you to turn in. This sheet, or a picture of this sheet on It's Learning. All right? Now, again, what do I want? I want your data table completely filled in. A good chunk of that we have done together. The last column is just a simple calculation of taking the absorbance divided by the molarity of your solution, of the trial, okay? So please do that manually if you could, by hand. The next part is way down in the bottom corner. I do want you to write in your molarity of Gatorade. The way you solve for that is by using the absorbance of Gatorade, which we just received from the spectrophotometer, which is 0.200. You'll plug in 0.200 for A, that's the absorbance, and you'll solve for C. We have the equation from our graph. That is written in red up above. And if I go back to the Google Sheet, right, this is what we did. Let me recap everything for you, because this is kind of a cool concept. It's a cool thing that we can do in chemistry using this spectrophotometer. We can solve for the molarity of an unknown solution by taking data on a known quantity of solutions, right? So we had our absorbance and our concentration. We took a whole bunch of different blue dyes and we made up a whole bunch of different solutions with varying molarities. We then measured the absorbance of those blue dyes at a specific wavelength. We used 560 nanometers for our wavelength. It's green light, but again, like I said in the beginning, if it was blue light, we would get readings that are off the chart and we can't actually record what we want to record. So we have all of these different solutions with different molarities of blue dye. We have their absorbances, and then we took the absorbance of an unknown. And the unknown, we can then use the relationship that we found from this data. Okay, so here was our equation, right here once more. We used the relationship of our data between absorbance and concentration for blue dye at 560 nanometers, and we can solve for the concentration of our unknown. All right, I hope that makes sense. I know today was a little more dense than the other labs. Again, if you have any questions, I'm hanging out in the building right now and you know, on Friday. So if you're watching this Friday during the day or Friday morning, I'm around. Please feel free to shoot me an email and I'd be happy to check in and help you out if you're struggling with this at all. But other than that, have a great weekend. We'll see you guys next week.